Good morning. Welcome to Krishna's Classroom. We begin with another episode of analysis on Rn. In fact, this is the 15th talk in this series. Recall that we introduced the concept of total derivative, and last time we also defined what the partial derivative is, which we are already familiar with. In fact, let us just recall E is an open connected subset of Rn. F is a map from E into Rn. So it's a map from Rn to Rn. Now we take Bn as an ordered basis, the standard ordered basis, namely E1, E2, etc. En of Rn, and Bm as a standard ordered basis, U1, U2, etc. Um of Rn. Now we use different notations for that. So we take or denote by F1, F2, etc. Fm the m components of F, because F is a vector valued map. Now, therefore, Fx is equal to sigma I equal to 1 to m Fix Ui, where Fi's are real valued maps from E to R. Okay, so this is what you have. Fi's are and one immediately observes that Fix is essentially Fx dot Ui, and for x belonging to E, j belonging to I belonging to 1 to m, j belonging to 1 to n, we define dj Fi at x to be limit t tends to 0 of Fi x tej minus Fi x divided by t. If the limit exists, then we denote it by djfi. Now you see that djfi is essentially the partial derivative of fi with respect to xj partial derivative of fi with respect to xj denoted by the partial derivative of fi with respect to xj denoted in this way. So this is the background. Now what we are going to do in this talk is to link up the total derivative with the partial derivatives. Now before that, we revisit some of the examples that we have looked at earlier and look at some of the inferences that we had. And this will give some insight into the sort of problems that you have when you work with partial derivatives. If the variable, if we are talking about a map from R to or some subset of R to Rn, then of course you can deal with almost the same way in which we worked with usual derivatives. And if you are talking about a map from R to R, then you see that the usual derivative is essentially the total derivative. Okay. So there is no complexity that comes from there. It's just a different wording that you use, that's all. Okay. So let us look at the following examples. I mean, these examples we have considered earlier. So let us work with the examples. This we have looked at earlier. The first example, or example 1, you have f defined from R defined by f of xy equal to 0 whenever xy zero zero, that is at the origin, and this is equal to xy square divided by x square plus y to the power 4 whenever xy is not equal to 0 0. That is for points not in the origin. So you are defining it in two different ways, one at 0 0 and the other one at other places, because you see that at 0 0 the denominator essentially vanishes. That is why we make a definition separate. What is the nature of this function? First of all, one can show that f is bounded. That's not difficult to see, because you can show that in fact that is f of xy mod bounded by half. That's very simple to work with. From the definition you can go, you observe that x square plus y to the power, so use However, you can easily show that f is not continuous. Zero. In fact, we make the following observation, that along all radial lines f is continuous at 0 0. Nevertheless, it is not continuous at 0 0. And this is quite easy to, so put y equal to, now this in fact takes care of all the lines of this. So y is equal to mx. This is y axis, except for the y axis. all radial lines. Axis for various values of m. Okay. Then you immediately see that this is f of and this goes to 0. Either, it doesn't matter. Okay. And along x equal to 0 and f of xy equal to 0 by definition. Okay, that is what you use, y not equal to 0. Then f of so all along all radial lines and along this line, along all radial lines and along this line, you see that the function goes to 0, and which is the value of the function, therefore it is continuous. However, y squared equal to x, which is this one, equal to, you put y square equal to x in this, therefore this is equal to x square divided by x squared divided by 1 by 2 for x not equal to 0. Therefore limit So you see that there is a path along which the function goes to half, which is not equal to 0. Therefore, the function is not continuous. At 0, 0. Now one can see, okay, what is the partial derivative of f? The partial derivative of f, see, is you take a point x0, y0. Suppose this is x0, y0. Then the partial derivative with respect to x is you allow the function to vary over along the line x equal to or y equal to y0. This is the line y equal to y0. And along this line, the function f of xy is purely a function of x, because you are setting y equal to y0, and then find the derivative of the function with respect to y, the usual derivative. So that would give you df by. Similarly, you keep the x coordinate fixed and vary the y coordinate. That means you set x equal to x0 and then allow, and then look at the function f as a function of y and then differentiate with respect to x at that point. So you have df by dy, df by xs This is quite easy to see, because you see that the numerator is a polynomial, denominator is a polynomial, and the denominator does not vanish except at the point x equal to 0, y equal to 0. So everywhere else it is well defined and they are all differentiable functions, and one can easily see that these partial derivatives exist. There is no difficulty. They are very nice functions. Okay. Now the only problem about the existence of the partial derivative is at the point 0, 0. So the question that you ask is, take it all this. So the only question that you ask is whether these partial derivatives exist at the point 0, 0, because you know that it is defined in a different way at 0, 0. It's not given in terms of this expression. So what do you have? Let us analyze this. It's quite easy to see this, because you So at 0, 0 we will examine this. We will do with the one derivative and the other one is simple. If you look at the function that you have is this. See, when f of xy this is the function whenever xy is not equal to 0, 0 and this is equal to 0, 0. That means the function is 0 here, everywhere else it is defined in this way. Now let us work out the derivatives. It's not difficult to work out the derivatives. Yeah. So how do you work with that? See, the variation when you take df by dy. See, you keep y fixed. So you are looking at the function along this direction. So it is along this direction that you are looking at the function, and what you have is you are interested at this point. So it is going to be, this is equal to limit 0 f of x 0 minus f of so you see that both fx0 is 0, f00 is this is equal to 0. So the derivative, the partial derivative df by dx at 0, 0 is 0. Similarly, this is also equal to 0, 0. Okay? Then you put x equal to 0 and then whatever be the function that you get, therefore this function vanishes, is 0. Therefore, the function both df by dx and df by dy exists in this case everywhere. The partial derivative although the function is not continuous. Therefore, the function f is not continuous. However, both the partial derivatives exist at 0, 0. That the point of the discontinuity, the point of discontinuity is 0, 0, and there both the partial derivatives exist, although the function is not continuous. Therefore, you see that the function is not differentiable. Not differentiable in the total derivative sense, but is not Frechet differentiable at, and one can easily prove that it is Frechet differentiable everywhere else. Okay, so that's the analysis of this example. Now we look at this one. Second example is gxy equal to 0 . This is equal to x y square divided by 6. Not equal to 0. You can make a similar analysis. Now you know how to work with it. The mode of working is essentially the same, and find out what exactly you can conclude on these functions. So what the outcome of this discussion is that the functions of several variables is not very innocent. Okay, they may appear to be nice in certain directions, but may not be quite smooth if you were to probe them along certain directions. Now this is the most important inference. Now you see that G is unbounded. I leave the proof to you. In every neighborhood of zero. It's quite easy to analyze this. All that you need is look at the case where x is equal to y cube. Okay, if you take x equal to y cube, what do you get? You get y to the power 5 divided by gxy equal to y to the power 5 divided by, so y to the power 6 for y not equal to 0. It's unbounded. So along that curve, and see, if you want to see what this curve is, it is this. I think we have looked at this. If you go to 0 along this curve, now you see that the function takes infinite value. But there are many other paths along which the function takes bounded value. So it is it's unbounded. And compare this with the first example. Now once again you can easily see that as you did here. The partial derivatives do exist, because the problem is this: partial derivatives, the limit that you take is not along this path. On the other hand, suppose you were to take a look at this function along this path and then take the derivative, because the function is unbounded, there is no question of differentiating it along that direction. So you take a parametric form of this curve. Now for instance, if you take this curve, what is this curve? X is equal to y cube. So you take the parametric equation, x is equal to t cube, y is equal to t. Okay, take this for t. Look at this function. Then what happens? You can write down gt. Once again you get this kind of scenario where the function is unbounded, therefore it is not differentiable along this path, at 0, 0. So see that the partial derivatives with respect to x and y do exist, because you are looking at taking into consideration only the variation of the function along the x direction and along the y direction, no other direction at all in this statement. Okay. Needless to say that the function is not differentiable, that is, it is not Frechet differentiable. Zero. Now let us take another example. The third example is zero. Here again you see that df by dy dx exists everywhere. That's quite easy to prove. You see that f is not continuous. Path x equal to y. And in fact, you see that f of xx equal to not equal to 0. And it is not equal to 0. Therefore, f is not continuous along this path. Therefore, once again, this function is not Frechet differentiable at. So, the moral of the story is that the existence of partial derivatives do not assure that the function is differentiable. Okay. Because the simple reason that if it is Frechet differentiable, then you see that the function is necessarily continuous. That's easy to prove. I think we have proved it earlier. Now the fourth example. Okay, we will take up this fourth example later. Now we just make a remark at this stage. This is the important remark. The existence of partial derivatives do not Frechet differentiability. So I will take up another example later, but before that we prove the other way around, namely that if the function is Frechet differentiable, then the partial derivatives exist, and we also establish the link or the connection between the two statements, namely the Frechet derivative and the partial derivatives. See, more examples, if you examine it, it will be really worthwhile, because you would get a insight into the intricacies of or what is in store when you consider functions of several variables, and how much restrictive is the differentiability condition, I mean Frechet differentiability condition. So the natural question that one starts asking at this stage is, how are these, the total derivative or the Frechet derivative is related to the partial derivative whenever both of them exist. So is it possible for us to infer that the function is a partial derivative exists? We have ruled out the other possibility. What is it? That existence of partial derivatives does not necessarily mean the function is Frechet differentiable. Naturally, ask the question, is the converse true? That means, suppose the function is Frechet differentiable, then is it do the partial the derivatives exist? Now this is the question that you are asking. So let us, in fact, we prove that it does, in fact, and we connect them up. So the following theorem does that. Suppose F maps an open set Rn into Rn and F is differentiable at a point x belongs to P. Then the partial derivatives dj fi at x exists and f derivative x is a linear transformation acting over Ej. This is equal to sigma ui. This is the relation between the total derivative and the partial derivative. Now you know that f derivative of x is a linear transformation from that you call. Now let us prove this. Now you see that ui's, ei's and ej's and ui's are as defined. Ready. So this is the theorem. This gives the connection between, that means the action of the derivative, f derivative on Ej is represented by this expression, namely dj fix acting over ui summed from I equal to 1 to m. Okay. So once we get this connection, now you can get the matrix representation for f prime in terms of the two bases bn and bm. That we will take up after proving this theorem. So let us prove this. Proof is very simple in this case. Fix j. Since f is differentiable, at x belonging to E, we have f x plus t ej minus fx, and what is this? This is equal to f derivative of x acting over the increment vector tj tj plus an error term t. Now you see that they are all vectors in Rn, because f is a map from Rn to Rn. Okay. So this is f dash acting over this. Now you see that this is a linear transformation. Therefore, what you have is this f of t times f derivative of x acting over ej and what is the property of R Tj? Where R Tj is the error term, has the property that norm of R Tj divided by T goes to 0 as 0. Tej is a vector along the direction Ej. Okay. So this one you take, and then you see that you can immediately write the following. So look at this term. Therefore, what it implies is the following. That is, what we have is this limit zero f of x plus t ej minus fx. What is this? You are just taking this and dividing by t. This divided by t goes to 0 as t tends to 0. Therefore, this term does not make any contribution. What contributes is essentially acting over. Okay. And you see that this is essentially this limit. The right hand side is then what we have defined as the partial derivative as dj djf, the partial derivative of the vector valued function with respect to j, or which implies for every component function fi of f dj further we have so this is the connection that we obtain, and this is true for all j okay. So that completes the proof of the theorem. So the important part is that this means that for all components this exists. Now you see, you have the expression, see, f derivative Ej is a linear, I think I should write here, not a derivative Ej, f derivative of x over Ej. See, f derivative of x and Ej belongs to Rn. Therefore, f derivative Pj belongs to Rn. And that vector is written in terms of this and is of Rn. That's what you see here. Okay. So this in turn, now we know the representations of linear transformations by matrices. So we are now asking what is the matrix representation. The matrix representation of denoted by Bm is given by is now you can actually write it up because we know how the matrix representation comes with respect to this basis. That's what we are trying to work out. Therefore, this one, that is these terms become the first column of the jth column. So you have D11 okay. So it's an m by n, m rows and n It's an m by n matrix. This is the representation. It is done in terms of what we call the partial derivatives. So this is the connection between the partial derivatives and the total derivative. Or now we can obtain the directional derivative vector h given by h sigma belonging to R. This is given by f derivative of x acting over the vector h, and this is equal to sigma I equal to 1 to n 1 to m sigma j equal to 1 to n dj acting over hj Now this is the directional derivative that we have. Okay, right. So that gives the complete connection between the total derivative and the partial derivatives. So if the function is differentiable or Frechet differentiable, then all the partial derivatives exist, and the matrix representation of the total derivative can be given in terms of the partial derivatives. The partial derivatives become what are called the components of the representing matrix. Now this is the conclusion. So remark: all the partial derivatives exist, and the matrix representation of f derivative can be expressed in terms of the partial derivatives. The entries in the matrix representation come from the partial derivatives. But the converse is not true. The existence of partial derivatives do not assure you that the function is differentiable, as we have seen from the examples.